Okay, we're going to talk about something called kinetic molecular speed. This has to do with the molecular speed of gas molecules. First, what we're going to do is we're going to talk about the 5 postulates of what's called kinetic theory. Okay, postulates of kinetic theory. So these are written out in your textbook and the PowerPoint slides. I'm just going to kind of abbreviate them and talk about what each of these means. The first one says that gas molecules are so small that their size is essentially negligible. So gas molecules are so small that their size is negligible. So it's so small that you can assume they don't take up any space at all. The second postulate of kinetic theory says that molecules move randomly in straight lines in all directions at various speeds. So I'm going to say molecules move randomly and in straight lines. The third postulate of kinetic theory says that the forces of attraction or repulsion between two molecules, we learned about this as intermolecular forces, in a gas are very weak or negligible except when a molecule collides. So I'm just going to write intermolecular forces between gas molecules are negligible. Meaning those attractive and repulsive forces between gas molecules are so small that they're basically zero. The fourth postulate says that when molecules collide with each other, the collisions are elastic. So what an elastic collision is, it's one where no kinetic energy is lost. So that means the amount of kinetic energy coming from one molecule when it collides with a second molecule, that amount of kinetic energy is just passed on. That's called an elastic collision. Fifth postulate of kinetic theory says that the average kinetic energy of a molecule is proportional to the absolute temperature. So I'm going to say average kinetic energy is abbreviated E sub K, is proportional to temperature. So these are the 5 postulates of kinetic theory. And when we're talking about gas molecules, we want to be able to calculate the speed of a gas. So that is mainly going to talk about number 5 here, that the kinetic energy is proportional to the temperature. So we're going to come back to that. Also, I want you to pay attention to these postulates. Number 1 and number 3, these are mostly true. The gas molecules are really small, and we assume they're negligible. The intermolecular forces are also really small. We assume that they're negligible. But in the next lecture on the van der Waals equation, we're going to see that these two are not exactly true, and we assume this to make some of our calculations easier, and we're going to see some differences in the next lecture. So just pay attention, be looking for that. So let's talk about how do we calculate molecular speed. Okay, calculating molecular speed. So the formula that we use to calculate molecular speed, the unit for molecular speed is U, a lowercase u, and this is what's called root mean square molecular speed. Which is abbreviated RMS, molecular speed. We'll probably just refer to it as molecular speed from here on out, but this is the whole name. So this is an average molecular speed at an average molecular kinetic energy. So the formula here is U equals the square root of 3RT over the molar mass of the gas. So let's break all of this down for a second. So we just said that U, this is the molecular speed. R, this is the molar gas constant. But because we're dealing with speed, speed is a rate. It's a rate that is going to be in meters per second. We need some sort of unit of energy. The unit of energy that we're going to get this rate from is something called a joule. Joule, Joule. And what a joule is it's a kilogram times a meter squared over a second squared. That's what a joule is. So our unit for speed, meters per second, is going to come from this unit of a joule. So because of this, instead of using the R that we used in the ideal gas constant, 0.0821 liter atmospheres per mole Kelvin, we're going to use a different R because we need a different unit. The R for this equation is 8.3145 joules per mole Kelvin. So you'll be given this constant. You're not going to need to memorize it, but what you are going to need to know is when do you use the R 0.0821 liter atmospheres per mole Kelvin, and when do you use the R 8.3145 joules per mole Kelvin. And the difference is the units. In this case, we're looking for a speed, a rate, has to have a unit of energy somewhere in it. This unit for the gas constant has a unit of joules in it. This is why I'm choosing this unit here. Do not use 0.0821 here. That would be the wrong unit and you would get the wrong answer. So again, this constant is now going to dictate all of the other units that we'll need. So this is going to be temperature in Kelvin. And now I have molar mass. So when you look up molar mass on the periodic table, you've only ever known molar mass to be in a unit of grams per mole. But we need to pay attention to this unit of joules here. So a joule is a kilogram times meter squared over second squared. So that means when you use molar mass to calculate molecular speed, you must convert molar mass from grams per mole to kilograms per mole. This is the only time you have to do this. This is something that everybody forgets. Don't forget to do this. The molar mass that you look up on the periodic table is going to be in a unit of grams per mole. You must convert it to kilograms per mole because this unit of joules, a joule right here, instead of this J right here, I could put kilograms times meter squared over second squared. And actually I will do that so we see how all of the units cancel. Okay, so this is the equation. This is what everything stands for. Let's look at a problem. So let's just say, what is the molecular speed of carbon dioxide molecules in a container at 23 degrees Celsius? What is the molecular speed of carbon dioxide molecules in a container at 23 degrees Celsius? Okay, so we're looking for molecular speed. We know molecular speed is U. Carbon dioxide, this is the gas. That's where we're going to get our molar mass from. And the temperature in degrees Celsius, we're going to need to convert that to Kelvin. So I'm going to write out everything that I know. I'm going to say U, molecular speed, equals the square root of 3 times R. And now when I write out R, 8.3145 joules per mole Kelvin, I'm going to separate out this unit of joules just so you all can see what's happening with the units. 8.3145, instead of joules, I'm going to write kilograms times meters squared over seconds squared. That's a joule over moles times Kelvin. So this is just, you don't have to do this. I just want you to see what's happening with these units. And then times temperature, T. So 23 degrees Celsius plus 273 is going to be 296 Kelvin. So that's the top, divided by the molar mass. So we need the molar mass of carbon dioxide. When you look up the molar mass of carbon dioxide, it's 44.01 grams per mole. You cannot use this, grams per mole, because this unit here of joules has a unit of kilograms in it. So you need to convert it to kilograms per mole. So there are 1,000 grams in 1 kilogram. So this is 0.04401 kilograms per mole. That's what goes down here on the bottom. So let's just look at what happens to the units before we do any math. Kilograms are going to cancel. Moles are going to cancel. Kelvin is going to cancel. What I'm going to be left with is meters squared over seconds squared, and I'm taking the square root of it. So it's going to be meters per second, which is a unit for speed. This is the square root of this whole thing, not just the top part. It's the square root of all of it. So this is how the units work. I write all of this out just because a lot of people will forget to convert the molar mass to kilograms per mole. The reason you have to convert it to kilograms per mole is because a joule is a kilogram times a meter squared over a second squared. So when you do all the math for this, you should get U, molecular speed, is about 4.10 times 10 to the second meters per second. In your calculator, you probably got 410 meters per second. This would have the wrong number of significant figures. This number only has 2 significant figures. When you put it in scientific notation, all of these numbers are significant. This 0 at the end of a number is not significant. This 0 after a decimal place is significant. This number has the correct number of significant figures. This would be the correct answer. 4.10 times 10 to the second meters per second.